Hi guys, today I wanted to simulate a single phase inverter, and as you may know, the inverter is a DC AC converter. So basically at the input you're gonna have a DC voltage, and so let me use paint for a bit. So at the input you're gonna have a DC voltage, and at the output you're gonna have an AC voltage. We suppose that the AC voltage is just a sinusoidal waveform, so we should consider also the possibility of a distortion factor, which we will calculate later with the command .4. Now, since the inverter will be driving a motor, the motor is an inductive load, so the output current will lag the input voltage. So this will be the output voltage, VO, and this will be, for instance, the output current, IO. From this graph you can understand that the inverter has at least 4 quadrants of operation. So when both the voltage and the current are positive, so this is IO and this is V0, you are in the inverter region, meaning that the power is flowing from the DC to the AC, and from the AC to the, also here, DC from AC. Now, when I0 and V0 are discordant in values, and you see in this in this interval here, for instance, then you have a rectifier operation, and the power is flowing from the AC to the DC. So this is the rectifier operation, and this is the inverter operation. We want to exploit the inverter, of course, in these two areas. Now let's simulate the single phase inverter. So as you may know, the voltage, the carrier voltage, is a triangular waveform with a sinus voltage, and this will generate a PWM which we will vary in accordance to the sinus voltage. So let's do that on the LTSPICE. So first of all, we want to call the parameters. The first is the modulation factor. So we need the modulation factor and the fundamental frequency. So .param f1 50. You are saying that basically the fundamental frequency is 50 Hz. Now you need the switching frequency of your converter, which we'll call with Fs. We will put 1 kHz since this is a high voltage application, and 1 kHz IGBT is a switching frequency more than enough. And then we use also the amplification, the modulation factor, AF, which is, for instance, 0.8. These are the parameters that you need. Now we want to generate our triangular waveform. Let's call it triangular. Let's just call it 3. And this will be also the node 3. Let's use the pulse, and to generate the voltage of the triangular waveform, just put a value between 0 and 1, and a rise and fall time of 1 over 2 times Fs. For the rise, and the same for the fall. The on period just 1 nanosecond, because you don't need something very, you don't need a spike so spiky, and a period of 1 over Fs. Now we want to use the control voltage, and as we saw from paint, this is the triangular voltage, and the control voltage is a sinusoidal waveform with the fundamental frequency of the circuit. So we will use instead a sinus waveform. We will use a sinus waveform with an offset of 0.5, an amplitude given by the modulation factor, so that by modifying the modulation factor itself, we modify the carrier with the switching with the fundamental frequency f1, and this is will be called the control A. Now, since this is an unipolar configuration, the control of the leg B will be the same of the control of the leg A, but with the inverting sign. So we will put the control B identical to control A with a biregular voltage BV, and the equation will be 1 minus V of control A. Now let's run the simulation for at least 1 milliseconds and let's see the results. So here we have the triangular waveform, so let's use 10 milliseconds instead. And these are the two sinus of 50 Hz. Let me put at least 100 milliseconds. Okay, so as you can see, this is the control waveform, and this is the control A, and this is the control B. Now what we want to do is to put a comparator in which we'll generate our PWM system. So we have to say that whenever the control voltage is higher than the sinus, a square waveform will be produced. How can we do that? Well, we can use the biregular voltage. So let's put the biregular voltage BV, and we will say that, let's close this, and we will say that basically if the control voltage of A is greater or equal than 1, than the triangular waveform, this will go to 1, otherwise will go to 0. And by saying just this, you are generating, as you can see, a variable square waveform which we will follow your control voltage. So as the control voltage approaches the 1, you can see that the square waveform has higher width, and instead, when you have lower values, the square waveform is smaller, as you expect. So now you have a variable PWM according to the sine waveform. And now the job is done, because what you have to do now is to put a switch, an ideal switch, and you have your single inverter phase or even a 3-phase inverter. Just put as many legs as you want. The 3-phase is a little bit different. I will cover that in another video, but for now let's just do the control just for the single phase inverter. So now you need to define your legs, which are given by the switches. So let's put switch 1, let's put switch 2, and let's put also the switches for the leg B. So this will be your first leg. The 3-phase inverter has 3 legs, and this inverter instead has 2. Each switch must be driven by a driver, but for now I will put just a variable voltage E1, which we will cover the problem of the high side switching voltage. Remember to put with the correct sign, otherwise it won't work. So now we are going to replicate this for each. This is grounded, but this is not. So this node here is grounded, yes, but the node here, but this node there is not grounded, because remember, this is a high side switch. So now you have dot model switch. We put up the best switch in our mind, 0.1 milliohm, and thereof with 10 mega ohm, and the threshold VT 0.5 volts. Let's put this somewhere in. And yeah, we can just replicate the system. I don't understand why there is a node here. There should be no. There should be a node. Okay, now this is correct. Let's put the gain as 1, and let's also put a protective diode here. This will be our ideal diode, and yeah, basically the circuit is finished, because now what you need to do is to replicate this for 4 times. Okay, now of course you have to modify the thing accordingly. So this is the high side, leg A, and this is correct. So if it is not, of course, the low side, you have to invert this sign here, otherwise it won't work. So whenever the first is switching, the other is not switching. So the sign is less or equal than, of course. This is an half bridge configuration, and the same here. So you have the control B, which is greater than the triangular waveform, and now you have the control B, which is less than the triangular waveform. So this is, do not copy and paste without thinking what we are doing, otherwise nothing will work. And so this can be grounded, because these two are the low side, and let's ground them. And now we have to connect your motor. Let's connect it here, and we have to supply also voltage, and let's put it there. Let's put 270 volts, and let's also put a bypass capacitor of 10 microfarads. Should be enough. Let's put our motor of the inductance of the motor, series resistor of the motor. Let's put -2, and the voltage. Pay attention that this is an AC motor, so you expect to have an AC voltage here. So let's put a sign with the fundamental frequency F1, 0 and 76 volts. 160 volts. Now let's shrink the circuit. Sorry, this is not connected, by the way, and let's connect this to this, and now let's run the simulation and see what happens. So this is the motor, this is the voltage across the motor, and you may not see, but this is an AC voltage, and if you check the current, oh, as you can see, the current is an AC. We have successfully converted a DC voltage to an AC voltage of your motor. So now your motor is supplied with an AC voltage, which is switching between -V in and +V in. So if I put 300 volt, it will be switching between 300 volts and -300 volts, because the control is unipolar. So now what we wanted to do is, you see that this current is more or less the current which is going at 50 Hz. So as you can see here, you see that the control voltage and in this current are a bit of delayed, and there is a bit of noise. So what we wanted to do in an inverter is to analyze the spectrum. So let's analyze the spectrum of this current and this voltage, and let's see what happens, because this is very, very interesting to do. So let's see the FFT of the current here. Oh, let's put in linear, and as you can see, you have a little bit of offset, and you have the major component at the 50 Hz, because this is the fundamental frequency of your inverter, and so you expect to have the major component at 50 Hz. And as you can see, 50 Hz, you have the major current. But there is a but, because as you can see here, there are also some harmonics. Oh yeah, and this causes distortion, noise, ripple, and whatever you want. As you can see, there is some noise at the 2 kHz, 4 kHz, 6 kHz, 8 kHz, 10 kHz, and all the multiples of the switching frequency. So what we want to do is to analyze better the the harmonic distortion of your inverter. And maybe there was something because there was some offset because there was also the transient. Maybe we can skip the transient to have a clean understanding of our let's see again. Okay, now this is now it makes more sense. As you can see, there is no offset because I don't expect the offset in there's so much offset in a sine. And yes, there are the harmonics. So now what we want to do is to study those harmonics. So as you can see, this is the voltage of the motor, and this is the current of your motor. Now what we want to do again is to study those harmonics. So let's call this by some nodes. This is node A, and this is node B, for instance. So now you want to use a behavioral voltage because you want the output of the motor to be available for study. So let's call this motor voltage, and let's plot the motor voltage with V of A minus V of B. Now you're wondering why I'm doing this. There is a reason for this, simply because now when you click it, you can immediately have the motor voltage, but not only for this, it's also because I want to study the harmonics. So now let's use the command for F1 1V of motor voltage. What we are saying with this command is to study the fundamental frequency of your output voltage of the motor. We want to do the same also for the current, and we will also do the same for the other harmonics. So dot for 1 I of L1, the current of your motor will be basically the current of your inductance, and also we also want to study the effect of the 3 first harmonics of the output voltage. Let's just use V3 instead. Sorry, I of should be the same. Should be correct. Now let's run again the simulation. Okay, nothing has happened. By the way, I forgot to check the switching nodes. So let's view this on the error log. Oh, so now as you can see, something is happening. So the harmonic frequency the first harmonic frequency, the fundamental frequency, is at 50 Hz, as we know. And this is given the value of the Fourier component, phase degree, normalized phase degree, and it is calculating the total harmonic distortion. So how the first frequency harmonics distort with respect to the others. If I'm not mistaken, the formulas should be 1 over VO1 of the square of the sum of V starting from 2, so the f of n, which goes to 0, from 2 to infinite. I don't remember if there is the square here, don't remember correctly. Let me check on the PDF. Ah yes, there was the square. So the output voltage is V O n square, where n starts from 2. So it is calculating the harmonic distortion. And the same happens for the others. So you have a 60% of harmonic distortion of the current, which is not so bad, and a 70% of harmonic distortion in the voltage. This is not so good. So let me also check how it is going the current. of the high side and the low side. As you can see, they are both in anti-parallel configuration. And also, let me check the 2 of the leg B. I think that we are done here. Thank you for watching. This is one of the most beautiful. I have to be honest that this is one of the hardest, one of the most beautiful simulation that I have done. And this is, don't take for granted this simulation, because it is true that they are very beautiful to do, but they are also they can be also hard for me to do at first without errors. Thank you for your attention, guys. See you on next video.